So, we are looking at prosthetic knee design, and to quickly recap, stability in the stance is important, and the swing control is also important. Swing control may be at a single speed, or if possible adapting to multiple speeds of walking would be desirable, so that a person can change their gait and have the prosthetic knee keep up with their walking, with whatever speed they are walking in. And in some cases shock absorption may also be incorporated in the knee. One level of shock absorption that is very important is when the swinging leg moves forward. Okay. So, in all these knees you will have an extension stop. Okay. So, in a mechanical knee, so the knee can't move this way. Okay. The knee can only bend this way. So, you will have what is known as an extension stop that prevents, that keeps the knee in full extension and not let it hyperextend. Okay. So, when the swinging leg contacts that stop, you need some dampening there, so that it is not an impact, it is not a hard impact at that point. So, you need some shock absorption. Other knees also, some knees may also incorporate shock absorption to in the form of some limited stance flexion, okay, like the knee does in the when we walk. So, that mechanism may also be incorporated in a prosthetic knee. So, the stability in the stance phase, as we talked about, can be achieved by different means. You can have actual mechanical braking mechanisms, which when there is weight on the knee, lock the knee, prevent it from flexing further. Or today we will talk about geometric stability, where geometry of the knee decides the stability characteristics of the knee. And then of course, you have microprocessor controlled knees, which use some sophisticated control mechanisms, usually with some kind of a hydraulic unit to control the knee movement and to make sure that it breaks at appropriate places. Okay. So, we talked about the extension assist, we talked about, this is the knee on the left, the geoflex knee, this is the simpler version of it. So, this version that is shown here has this stance flexion feature. Users are not very comfortable with that stance flexion. It gives them a feeling of instability sometimes, because if they are not used to that, if it is a new prosthesis user, they can be trained and they may actually benefit from having that. But an experienced prosthesis user, because a lot of knees do not have this stance flexion feature. So, suddenly when they are, so they tend to keep their knee well extended during weight bearing. So, if they feel this slight movement in the knee, they have this feeling of instability. So, for them there is a different version of that same knee, which is without the stance flexion. So, this is an example of, we will talk about polycentric knees in a, but you can have a wide range of knees. You have what are known as single axis knees. So, if you can classify knees, you see that you can have single axis knees, you can also have polycentric knees. So, a simple hinge, a single axis knee is essentially just a simple hinge. Okay. It allows that single degree of freedom, flexion and extension. And so, it is basically just a nut and bolt, just a revolute joint that is between the thigh portion and the shank of the prosthesis. I need the prosthesis. So, you have just a simple hinge, and then you could have what are known as polycentric knees. Now, these are knees that have a moving center of rotation. So, what this means is, so between you have the socket and you have the shank. Between these two you could have just a simple hinge joint. So, the socket or the thigh rotates about the shank, about that single joint. A polycentric knee is one where the center of rotation of this thigh portion with respect to the shank keeps changing. It is not a single point, and we will see what are the advantages of that. Now, your actual human knee itself is not a simple hinge joint. Okay. If you look at the human knee, right, you will see that as this moves, the knee center, the point about which the thigh is rotating about the shank is actually changing. You have it forms a small semicircular arc. Okay. It is not a constant point, that is why you have both sliding and rotation. You do not have only pure rotation at the knee. If you had only pure rotation, then it would be a single joint, a single axis joint. But actually here the instantaneous center of rotation changes. Okay. So, they can do some experimental studies to find out what, and this actually looks more like a this kind of a small, this is the locus of the knee center in the human knee. But in usually that the range of motion of that instant center is very small. So, it can be approximated, especially for a prosthesis, okay, because there is nothing in the case of an orthosis, approximation can cause some problems, because your actual knee, which is in the supportive braces, is moving with this kind of a knee center, and now if you force the braces to move about a single axis, that causes relative motion between the device and the person's limb, and that can sometimes lead to discomfort. That is called pistoning, that is called a pistoning effect. But in the case of a prosthesis, because there is nothing there, you can approximate this to a simple hinge joint, okay, a single axis hinge. Okay. So, in many cases the simplest type of knee is your single axis knee. Okay. So, now let us see what we saw, that in some cases a locked knee is the solution that is used, but as we saw, the locked knee is not always a good solution for walking, because it causes that circumduction kind of gait or some other compensation that the person will adopt, and which can lead to increased energy consumption and also unnatural loading on the other joints, leading to degeneration. Okay. So, let me just try to explain it with this. The video will actually show it nicely. When the person using an above knee prosthesis, say with a single axis joint, you have a single axis joint here, okay, at heel contact, at heel contact, the load line, okay, say is like this. Okay. Now, what is the tendency of the knee? What kind of a moment will it cause about the knee? This is going to cause a flexion moment about the knee. So, if the person does not apply any moment here at the hip, then the tendency of the knee is going to be to buckle. Okay. So, now what the person has control over on the prosthesis only through the residual limb that is there, right, that is housed in the socket. Now, what the person does is the person applies a hip extension moment. Okay. So, the person applies a hip extension moment at the time, and what that does is this moves against the, there is an extension stop, right. So, it will tend to lock the knee against the extension stop, and essentially what that will do is now the person is pushing back on the ground with their heel. When you do that, when I extend my hip and lock the knee, I am pushing back against the ground, and that creates a forward force which changes the direction of this ground reaction force. This will move in front of the knee joint, okay, because I have this original thing plus a forward force which changes the direction of the ground reaction force now, so that it moves in front of the knee joint. So, when the load line, the load line is this line through which the ground reaction force acts, when that is in front of the knee, you have an extension moment about the knee which keeps the knee stable. Okay. So, by applying this hip moment, if the person was not able to apply that hip moment, then this is a problem. But they may have some residual hip strength and they can apply that hip moment and cause this load line to move in front of the knee. Now, at toe off, to initiate swing, you need the opposite. At that time, if you look at the load line is actually in front of the knee, okay, which means that the knee is locked. But what do you want to do when you want to go into swing? You want to unlock the knee. So, in this case, the person applies a hip flexion moment. Here this was a hip extension moment. Now, the person applies a hip flexion moment and that moves the ground reaction force behind the knee joint, which will initiate flexion, because now the loading is the loading is lower on the leg. So, they want to initiate flexion. So, they move, they exert a hip flexion moment which causes the load line to move behind the knee joint. This hip flexion moment will cause the load line to move behind the knee joint and initiate flexion. So, this is initiation of flexion, knee flexion. Here you want to perform knee extension.
Here mechanical lock is to prevent hyperextension.
Mechanical lock is only to prevent hyperextension. Okay. So, the knee extension from to prevent it from buckling, that has to be controlled by the hip. So, we do this when we walk to some extent, we apply this extension and flexion moment. Of course, we have control over the knee, the knee flexion is controlled. So, we do not have, but a person with an amputation necessarily has to apply a hip extension moment at heel contact and then a hip flexion moment at toe off in order to initiate knee flexion, to initiate swing. So, what this does is, we know that if with the application of this hip moment, if they are able to move the load line to this place, then as long as the knee is located behind this line, that is my stable region, right. As long as the knee joint is located, if I am using a single axis knee, as long as the knee is located behind that load line, that is my zone of stability. Now, if I look at, so this is at heel contact, at toe off, by applying the hip flexion moment, so this is by applying the hip extension moment, okay, hip extension moment, and here I apply. So, when I apply the hip flexion moment and I move the load line, so if this is the reaction force, I move the load line behind the knee. As long as the knee is in front of, anywhere in this region, in front of this, I can initiate flexion. Okay. So, this, if I superimpose these two on this diagram is those two superimposed. So, then I get what is known as this zone of voluntary stability. So, what that means is, so that is the region that overlaps. If the knee is located in that region, in this cross hatched region, okay, where the two meet, in that common region if the knee is located, then with my hip moment voluntarily I can control stability at heel strike and initiation of flexion, okay, initiation of swing. Okay, I have the ability to control that. Now, what happens is, so this is with, if I am able to apply normal levels of hip extension and hip flexion moments. Now, for a person who has impaired hip musculature, it could be because of atrophy, it could, because of amputation, because of whatever reason, this zone, because they are not able to move it when you superimpose the zones, okay, because the amount of moments they would be able to apply are lower than an able bodied person, this zone shrinks. Okay. So, you can see here that this zone is smaller than the zone in a person who has normal hip strength. Okay. So, now what happens if you locate your single axis joint. So, in many cases if there is a single axis joint, what they will do is they will actually locate it slightly posterior from the hip ankle line, for instance. Okay, if this is your hip ankle line, the alignment of the knee will be such that it is located posterior, could be 10 to 15 millimeter posterior to that line. Why would they do that? Because at heel contact, you are ensuring that even with minimal hip strength, the knee will remain behind the load line. Okay. So, you are actually offsetting it from where the normal knee would be to ensure stability at heel contact. But what does that do to initiation of swing? Now the knee is hyperstable at toe off, right, it is further behind where it should normally be. So you can see here, even though this knee location is in the area where it would provide stability, for initiation of swing it does not lie, this is the common region. Okay. This knee is stable, it is still in the stable region, in this cross hatched region. Okay, it is located. So, it will provide stability at heel strike, but initiation of flexion becomes very difficult. So, at swing they will have to really completely unload the knee before they can flex the knee. Again that leads to an unnatural gait. So, they can't, because the knee will stay locked. As long as there is any load on the knee, it will be very difficult to flex the knee, because the knee center is now even more posterior than the normal case. So, a single axis knee obviously. So, now the other option is, okay, if I can't have a single axis knee here, and if this is the zone that I have, then perhaps I should locate my knee somewhere here. It is a possibility. If I locate my knee there, then with whatever muscle control I have, I can control the knee. So, my socket would still be like this would be my knee, and my shank would be like this. What is the problem with this? When you sit down, your thigh is going to project. You cannot sit normally with a single axis knee in this kind of a location. So, now what do we do? This is how the evolution of a polycentric knee happened. Okay. So, if you look at the zone, you want the knee to be located there, but you also want the knee to move somewhere down here when the person is sitting, when the knee is flexed 90 degrees, so that it appears normal. So, really what you want is a moving knee center. At full extension, when the knee is fully extended, a rather high location of the knee is desirable, so that the person, the prosthesis user, can control the prosthesis better by applying their hip movements. But location of a single axis knee there is cosmetically unacceptable. So, that is how the polycentric or the linkage type knee evolved. Okay. So, in a linkage type knee, instead of a single axis, okay, say you have the simplest type is a 4 bar linkage. Okay. So, I have these 4 links L1, L2, L3 and L4. L3 is what is attached to the socket. L1 is attached to the shank. Okay. So, you have 2 links, you have this linkage, instead of directly connecting the socket and the shank with a single axis knee, you have these 2 additional links in between. And what does that do? Now, what happens is, if you remember your K-DOM, okay, kinematics and dynamics, you saw that if you have 4 links like this, okay, then say this is 1, 2, 3, 4. At any instant 3 is rotating about 1, okay, 1 is the fixed link say. Okay. So, with respect to 1, 3 is rotating 3 is motion can be described as a pure rotation about the instant center I13. And how do you find instant center I13? You extend link 2 and link 4, and where they meet, that is your instantaneous center of rotation of link 3 with respect to link 1. Now, in this case, what is my link 3? My link 3 is my socket and thigh. What is my link 1? My link 1 is my shank. So, what does I13 become? It is essentially my knee center. So, that is my virtual knee center at that particular instant. And now what? So, with this 4 bar, with this kind of a linkage, as link 3 moves, as it flexes, right, as the socket flexes with respect to the shank, what happens to this instant center? It does not stay the same, it keeps changing, because every time those two links, the intersection of those two links gives you the instant center. Then what happens is, if you plot, so at 0 degrees of flexion, that is if the angle of link 3, the socket with respect to the shank is 0, then this is the location of the instant center. So, I can locate it fairly high and also maybe behind the load line at full extent. Then as the knee flexes, you can see that it rapidly moves down. These points, these indicate the degrees of flexion. This is just some random geometry, okay, of the linkage. But you can see that it moves down, and so say at 120 it comes very close to where the anatomical, so beyond 90, it's when it crosses 70 something like that, then it is always in that region near the anatomical knee center. So, what that does is, so here for instance you have this link, so you have the 4 pivots here, okay. So, this is link 1, your shank, this part is rigidly attached to the shank, so it forms part of the shank, this is your link 1. So, let us call this link 2. Link 3 is rigidly attached to the socket, and this is link 4, okay, it is a planar mechanism. So, now if I flex, okay, the instant center at this point is the intersection of these two, it is somewhere located somewhere here, okay. So, I can flex with minimal effort, okay, and then as I bend, you can see that now the instant center is at the intersection of these two links, it is somewhere here, which is close to the, so for sitting it looks fairly normal, right, you do not have the cosmetic appearance is very much acceptable. So, this is, and this kind of a knee therefore provides a mechanical advantage. So, for a person with reduced hip effort, they are now able to control the knee better, control the stability as well as the flexion of the knee. Now, of course, as the geometry changes, so different 4 bars will have different characteristic instant center curves. It is not going to be the same for every 4 bar, because it really depends on where these 4 pivots are located. So, this is an example of geometric stability. There is no braking mechanism in this which is providing the stability. The stability arises because of the geometry of the mechanism, and by designing it with appropriate geometry, you can ensure the stability of the knee for the user depending on their residual strength. So, this is an example of a polycentric knee. Okay. So, here again you see it is a 4 bar with a different geometry, and that is the advantage. So, even though it does not look like a normal knee, it does not look anything like a normal knee, okay, and it does not even follow the pattern, the motion of the normal knee. But here what you are doing is you are providing some compensation, you are providing a mechanical advantage to the person using the knee, because they have some impaired musculature, because they do not have the same muscle strength, you are compensating for that. So, here is an example where you are not just mimicking, you are not even mimicking the motion of the knee, but you are actually providing some kind of an advantage to the user to compensate for their impairment. So, this is the reason why something need not always be biomimetic, just as you saw with the prosthetic foot. It need not look like the foot, it need not even function just like the foot, as long as functionally it accomplishes the same goals. Okay. So, here functionally for walking the goal, or even for standing, the goal is to ensure stability with minimal effort. Okay. And then for smooth walking you also need to be able to swing the leg forward. So, this provides both of those functionalities without looking like the normal knee and without having all the other contraptions of the that are needed to control a normal looking knee. So, if I designed something that looks like the normal knee, control of that would become much more complex. You saw even with the single axis knee, while it is a very simple design. So, this is one level of complexity, this is a higher level of complexity in the design. So, but a 4 bar is still relatively easier to maintain. Some of these 4 bars still may have only frictional swing control, but they still function significantly better than a single axis knee. They can provide better functionality, especially if you are on uneven terrain and things like that. Stability is very important. How much you can voluntarily control the stability is a key aspect of the knee. So, you can see here there are various geometries of these 4. This one is actually a 6 bar knee, it is a more complex mechanism, and this knee actually, instead of using a typical 4 bar. So, you will see most of the knees are these kinds of 4 bars, okay, where when I say 4 bar, one is the shank, one is the thigh, and then you have 2 links, and we treat it as a 4, even though you have 2 and 2 of each. If you look at it from a kinematic perspective, it is just a planar 4 bar mechanism. It has more links, but that is for stability in the it is for structural stability in the other planes, in the frontal plane as well as the transverse plane. You can't have just a planar mechanism, because that will not be able to sustain the loads in the other planes. So you basically duplicate that linkage on the other side to achieve that, but kinematically it is just a 4 bar. This and this 4 links is what. So, different geometries are there, and always if you look at the linkage, it only the pivots are what matter. The shapes of the links do not really, the shapes of the links are for other reasons, to ensure that it clears properly, and it to ensure that you get sufficient flexion of the socket and things like that, but they are not really. The pivots are what determine the geometry of the knee. This knee here, and this is what it looks like on the inside. This is to show you that this knee is not a 4 bar, but this is also a polycentric knee, and this is actually an inverted slider crank mechanism. So, instead of so it achieves the same. So, you still get that kind of in fact this is a very stable knee, because if you look at the instant center curve, the knee center remains behind the load line. In the case of this kind of a regular 4 bar, so if this is the anterior direction, this would be the anterior, this would be the posterior direction. Okay, this is my AP direction. So, as this bends, okay, this knee center moves rapidly down and forward. In the case of this mechanism, okay, so if this would be the anterior direction, as this bends, okay, this it has a curve such that the instant center moves like this. It stays behind the load line for a greater range of flexion, this type of a design. Okay. And the advantage is that it provides, so even if the person lands on a slightly flexed knee, okay, they can quickly recover, because it tends to be inherently more stable. This has some other disadvantages. But stability wise, so especially for elderly people, this kind of a knee is very useful. It provides them that additional stability. It has a slightly different, so it uses an inverted slider crank instead of a regular 4 bar. An inverted slider crank is also a version of a 4 bar, because a slider crank is nothing but a 4 bar with one pivot at infinity, and an inversion of that is again belongs to the family of 4 bar. So, this is so you will see that there are knees with very different geometries. These are a couple of knees that recently have been, they say they have designed it for developing countries, and mainly what they have tried to do is minimize the cost. So, they are using plastics, they are using molded, injection molded plastics and things like that too, because obviously this kind of a knee would be more expensive than your simple nut and bolt, your simple knee bolt, right. So, these but since a 4 bar since a polycentric knee has advantages, they have tried to come up with these designs for developing countries. Unfortunately, they have not really looked at the functional aspects so much. They have focused predominantly on the cost reduction, but they have pretty much they have not really paid much attention to the geometry of the knee and whether that is suitable for the developing countries. And that is one of the things we did when we looked at all the existing geometries and then decided to design our own knee here. The other advantage, let me just quickly show you a video. So, if you look at, so we looked at all these different knees, many of them are commercially available, and then we looked at, this was the first prototype that we built, Proto 1, and then so we looked at various parameters, we identified various parameters related to what affects stability in a polycentric knee. Okay. So, one is what you call the effort at heel contact, then the effort at push off. Do not worry about what this x and y, those of you who are interested can read this paper, but x by y is sort of a ratio that denotes that shows what this heel contact effort will be, the muscular effort required. Then something called the stable knee flexion range. So, up to what amount of knee flexion So, even if the person lands, because that is very likely, if you are walking on uneven terrain, it is likely that every time you complete swing your knee may not be fully flexed, and you land, you may contact the ground before you are fully extended, before the knee is fully extended. So, up to what flexion can that happen, and you will still be stable. So, different things like that. And maximum overall flexion, as I told you, since we do not in developing countries we do not always sit in chairs, for social things we may need to or we may be in more cramped spaces, like even in the classroom here you do not have a lot of leg room. So, you may not be able to sit, you may have to actually flex your knee more to sit comfortably, or in a small car or in an auto, okay? Places like that. So, the amount of knee flexion that is required, maximum knee flexion that is possible, the requirement is greater. So, you can see here that you can have a lot of knee flexion. So, it is in many cases it is limited of course by the socket. When the socket contacts the knee, that is when your knee flexion stops, that is when you get your maximum knee flexion. But what happens is, in many cases in the commercial knees, they will only report, we found that they report things like they report high values of knee flexion, but if you actually put a socket on it, so now without the socket I can get this much knee flexion, right. This is not a commercial knee, but still I can get this much knee flexion, right. But if I put a socket like that onto this, then I might only get about 90 degrees. That is what happened with our first prototype. Okay. When we looked at it, I mean it is the mechanism itself, if you look at it, you get this much, but practically we were not able to get more than 90 degrees. And the same thing with other knees. So, in the market many of them will report knee flexion like this, they will say 160 degrees of knee flexion, but whether it is practically achievable is a different story. So, when we did our optimization, we took a socket, we took like a spherical socket and then compared the knees. If all of them were fitted with the same socket, then what would be the maximum knee flexion that you would get, taking into account constraints like this. So, we did an optimization of all these using all these different parameters and constraints, and the red one, the goal was, so if you look at this radar diagram, whichever knee has the best score. So, we compared the scores on all these 6 counts. This is just one method of comparison, and there is no weightage or anything, a specific weightage here, assuming everything had equal weight. We said okay, the best knee gets a score of 2, okay. The worst knee gets a score of 1. Okay. So, in this diagram we just graded it like that, and so the objective is to get as much area as possible. You want to reach out to all 6 corners, you want to be the best on all these parameters which are which we identified as something for walking on uneven terrain. And then we came up with this red one. The red knee is this R2D2 knee. That is the knee which provided, that is the geometry which provided this the maximum score on all these counts. Now, you can have other addition. So, in the next level we may actually add some more parameters, like we have now studied the swing behavior some more in our research, and we found that maybe we can add 1 or 2 parameters to the optimization to get even better performance. Of course, you can keep improving, or you can say at some point, okay, I have something that is fairly good and the goal is now to get it to the market. which is what we are working on now. Because you can keep improving something, but at some point if you want it to actually benefit someone, you are going to have to say, okay, now I will stop here and take it forward. If it is just an academic exercise, you can keep optimizing, you can keep coming up with 10 more parameters, you can keep doing that. But practically you have to stop somewhere. So, if you look, the other advantage of polycentric knees, the other big advantage of polycentric knees is that because of the linkage configuration, as the knee bends, okay, the distance, this shank is actually shortening. Okay. So, because of the linkage configuration, if you plot, it is called the shank shortening effect of a polycentric knee, and what happens is, if you measure the distance, the overall limb length from the hip to the toe. Okay. So, from the hip to the toe, so here, and if you plot that as the knee flexes, you will find that it is shorter than in the case of a single axis knee. So, if you use a single axis knee, so what that tells you is you can get greater toe clearance with a polycentric knee. So, this is a known advantage, this is another known advantage of a polycentric knee, that you can get greater toe clearance, which again facilitates better walking on uneven terrain. So, you can get anywhere 20 to 40 millimeters more than a single axis knee. Again it will depend on the geometry of the knee. So, you can see here a single axis knee, the black one versus the blue one. So, with different degrees of flexion, you see that this you get better toe clearance. Okay. And that was the other parameter we used for comparison, that was one other parameter we used for comparison among all these different knees. Okay. Which one gives the best toe clearance? How do you maximize the toe clearance? So, now the reason you are not able to hit all 6 is many of them are competing measures. Okay. Many of them are competing quantities. So, you gain on something, you are going to lose on something else, and that is why if you see the red one, it does not hit the maximum on any individual parameter, whereas some of these others hit the maximum. So, even the first prototype, for instance the stabilizing hip moment or something, it was the best, but its problem was maximum overall flexion was very limited. So, there it got a 1 or a it was the lowest of the lot in that one. So, you can see that since these are competing measures, some other knee may have had, like this blue knee had a very good maximum overall, many of them had high knee flexion, maximum overall knee flexion. This one also had this knee here, which I also have. This is the this is actually a 4 bar knee which also has a pneumatic unit here. So, it is actually a 6 bar if you consider the pneumatic unit, the piston and cylinders. So, this is a knee that is a 6 bar knee. So, you can see here there is a there is a 5th link and then a piston that goes into a cylinder. Cylinder which is housed in this shank. So, this is a 6 bar knee, but functionally as far as the instant center is concerned, it is basically a 4 bar. So, it would function even without those extra 2 links. The extra 2 links are for the swing flexion, to control the swing flexion and extension, not the, they do not influence the geometric stability of this knee. To find the knee center, you would still use only this 4 bar portion of the knee. Okay. So, a polycentric knee can provide more functionality than a single axis knee. Okay. Tomorrow we will talk about this the more sophisticated microprocessor control knee, and then I will tell you about a few other assistive devices to wrap up the course. Okay.